General Chemistry, Lecture 6, Equilibrium. What does equilibrium mean? Well, equilibrium states that when reversible reactions are proceeding, they will reach a state with minimized energy and maximum entropy. That is, they're balanced, meaning that the concentrations of reactants and products remain constant. Dynamic equilibrium is stated as the rate forward equaling the rate reversed, meaning that they're still proceeding. This is different from a static equilibrium, though, where they're completely stopped. If we were to think about how equilibrium affects normal systems, it has everything to do with science as we know it. Nature likes to keep a balance, and that's where equilibrium comes into play. The premise of equilibrium is based on the law of mass action, which states that if a system is at equilibrium at a constant temperature, then the following ratio would be constant, or the KEQ. For any chemical reaction noted below in the form of A, B, C, and D, the equilibrium constant KEQ is going to be set such that it is products over reactants. So to simplify KEQ, it would look something like this. Concentration of products, concentrations denoted by brackets, over the concentration of reactants. This will be true no matter how complicated the reaction is, so bear that in mind. A reaction quotient, on the other hand, noted as Q, is a snapshot of the reaction at a given time. The Q quotient, or the reaction quotient, is noted and written as the same as KEQ. However, KEQ is signifying equilibrium, whereas Q is talking about the reaction at a given moment. If it's less than K, then that means that the reaction is proceeding forward, with a delta G of less than 0. If Q is set to K, then that means that the delta G is 0, and the reaction is at equilibrium. This is pretty obvious, since if Q equals K, then that means the Q expression is the same as the KEQ expression. If Q is greater than K, that means that delta G is greater than 0, and the reaction is proceeding backwards. The reaction quotient is a good way for chemists to look at a system and to see if equilibrium has been reached, or if it's still not there yet. Perhaps one of the most pivotal principles in chemistry is Le Chatelier's principle, and that's something we're going to go into next. By definition, Le Chatelier's principle states that chemical systems will always try to restore equilibrium when under stress. There are different types of stress, though. The one that's pretty obvious is when there's an increase in products or reactants. If you increase those, it's going to push to the other side. So if I were to write out a very simple reaction of A plus B to C, if I were to increase the concentration of A, the system is going to be pushed in a state of stress. Therefore, the reaction is going to favor the formation of products. The same is true if I were to increase the concentration of C. Since there's an overhang of products, it's going to proceed the opposite direction in favor of the reactants, trying to restore the balance that it had previously. Increasing pressure on a gaseous system is going to shift the reaction to the side with the fewer moles of gas. What I mean by this is if I were to have too many moles on one side, so if I were to write out something simple like this, let's do, how about nitrogen gas plus hydrogen gas, and it goes and makes NH3, and this is going to also be in the gaseous state. If I were to increase the pressure, this would favor the products because there are fewer moles on this side. And if I were to decrease the pressure, the opposite would occur. Just out of curiosity, how do you think pressure and volume are related? Well, if I increase the volume, I'm also decreasing the pressure. And decreasing the volume is going to increase the pressure. So if I increase the volume, it's going to favor the side with the more moles, and decreasing the volume is going to favor the side with the fewer moles. So if you think about it, pressure is going to affect the system by an increase favoring the side with fewer moles. However, volume is the opposite. If you increase the volume, it's going to favor the side with more moles. The last type of stress we're going to go into is heat, or temperature. For these, you treat heat as a reagent. So if it's endergonic or exergonic, it'll shift if heat is added or removed, respectively. So if I require heat to be put into my reaction, so if I use my AB example, if I increase the heat, it's going to favor the formation of the product because there's going to be more of a, quote, reactant on this side. Subsequently, if I decrease the heat, it's going to go the opposite direction. This is if it requires a heat input. Now, the other type we're going to look at is if heat is a output. So, if the reaction gives off heat. If I add heat, it's also going to favor the reactants, whereas if I take away heat, it's going to favor the products. So in this sense, you just treat heat as a reagent, just like you would a reactant or a product. Equilibrium is very crucial for all types of biological life. If you look, all natural systems are going to be pursuing a form of equilibrium, including our bodies. However, we're forcibly keeping our bodies out of equilibrium. If a biological organism ever does reach equilibrium, then they are dead. So, when we're looking at the premise of equilibrium, we have to think about what it means in terms of chemistry and biology at large. We'll finish our discussion of equilibrium there. In the next lecture, we're going to go into some thermochemistry, and we'll see you then.